Hello, this is March Patel, and today we're going to be finishing up Unit 13, which is all about acids and bases, and we're going to be talking about titrations. And so, first, before we talk about titrations, you have to know what neutralization reactions are. And so, remember, a neutralization reaction is when an acid and a base react to form a salt and water because they sort of neutralize each other because the the acid donates its hydrogen to the OH and forms water, H2O, and this Na and Cl are left alone. They bond and form ionic bond, which remember are always neutral. And so in the end, the product is always going to be neutral, so neither acidic nor basic. So neutralization again is a reaction of acid and base making a salt and water. And so now we're going to be talking about what a titration is. And a titration is practically a neutralization reaction, but it's controlled. That's an important part. So a titration, the definition is an analytical technique used to calculate the moles of an unknown. So here we have a burette, and inside we have a titrant. So we know the concentration and the milliliters of this because of course we have it in a big tall like test tube sort of thing, and then we have a stopcock here, and so we control the amount of liquid that goes down into the beaker or into the analyte, and we do it until it's at an equal concentration of both of them. And so we have a known volume and known concentration. In the analyte, we know its volume, but we don't know its concentration, and so we can sort of use algebra to solve for it. And easy way to calculate the moles of unknown is using this simple formula. Molarity of A times volume of A equals molarity of B times volume of B. And we can only use this when it's a 1-to-1 mole ratio. Otherwise, we have to use stoichiometry because it's a different mole ratio. And so now we're going to be talking about some terms about titrations. And then one is there's an equivalence point. And so equivalence point is when there's equal stoichiometric amounts or moles that react completely. And remember, in equivalence point, it sounds like equal. So the moles of H plus and moles of OH are exactly the same. So hence equivalence point. And so here are some chemical equations. We're going to have three, and we're going to see if moles of H and moles of OH are equal using subscripts and coefficients. So here we have a coefficient of 1 and a coefficient of 1, and there's only one H and one OH here. So this in fact is equal, so we could use this formula. Then in the second one, we have 2 moles of this and 1 mole of this. So this is not equal, and so we can't not use this because remember, to use MVA equals MBVB, we have to have a 1-to-1 mole ratio like this one. So this one we cannot use, but in this one we also cannot use it because even though there's no coefficients, both of them have one coefficient. This one has 2 hydrogens and this one only has 1 OH, so they're not equal at all either. So remember, when you're using coefficients and subscripts to tell, a key thing is that they both have 1 as their coefficient and they have no subscripts, and that's when you can use this formula for sure. So this one also you cannot use because there's 2 hydrogen for every 1 OH in 1 mole. So this would have a mole-to-mole ratio. And then we're going to talk about what an endpoint is. And the endpoint is, so here the endpoint would be when the indicator permanently changes color. So which of these three would be the endpoint? And just from this definition you can probably tell this one it's changed permanently. So here we have a clear substance here. If we, like when you do a titration with phenolphthalein, when you swirl it around, when it's a little bit of pink, it'll turn back to clear. So that's not permanently changed. But eventually you reach a point where if you drop like maybe 3 or 4 drops, the whole thing turns pink automatically like that. And so that's called equivalence point. And so, end point. Sorry, end point. That means end point. When the indicator permanently changes color. So a common indicator we use for titrations is phenolphthalein. And so phenolphthalein is clear in acid and it's pink in a base. So it's often useful when we're trying to find the concentration of an acid because it's clear in an acid. So when we add a base to it, once it becomes a little basic, it'll turn pink. So that's why phenolphthalein is used. And so remember solution stoichiometry. This should be a review for you. And remember that we had this whole like map. And so we had grams and we used molar mass to convert to moles. And then we also use molarity from liters to moles. And from moles to moles, we can go to substance B and then we can do the same thing. We can go back to grams using molar mass or to liters using molarity of B. And so now, like, take this map and now, like, forget about grams. So just forget this whole left side. And so this is what solution stoichiometry is all about. Just using liters to moles, mole to mole ratio, and then moles to liters of B. So we're only going to be using this side. And again, there's some, like, the maximum steps we can do is 3. And the least we can do is 2. And we'll be doing some problems using this. So don't freak out. And I'm sure most of you already know just from stoichiometry that this should be very familiar to you because we've done it before. But now we're just going to call it titrations instead. So not much of a difference. So here we have an example. Hydrobromic acid is titrated to equivalence with sodium hydroxide. So what volume of 2 moles of HBr is needed to react with 10 liters of 2 molar NaOH to what is the volume? So to get neutralized. And so here we have to first extrapolate or take out what we have. And so we have 2 moles of HBr, so that's the molarity, and we need to calculate volume. So off to the side you can write that we need liters of HBr. So until we see that in our formula, and then we're done. And we have volume of the NaOH, and we have the molarity of NaOH. So we have these 2 knowns, and we need to solve for this. So first we start with what we have. So we have the volume of NaOH. So that will be substance A in this case. And so the reason why we have BOH is because it's base and oxide, so hydroxide. So that's why we have OH over here, BOH. And so we have 10 liters. And now we want to go to moles, so we can use mole to mole ratio. And so to go to liters to mole, we use molarity. And we want liters on the bottom, so liters cancel out, and we're left with moles. So we have molarity. So blank moles per liter. And we always get molarity. It's always provided from the equation. So it happens to be 2 moles per liter. So we write 2 moles in 1 liter. Like that. And so liters cancels out, so we're good. Now we're in moles of NaOH. So now we want to go from NaOH to HBr. And what do we use? Did you say mole to mole ratio? And if you did, you were correct. So we use mole to mole ratio, so we know what goes on the bottom from the previous fraction. So because moles of NaOH is on the top of this one, we want to cancel out. So we put on the next fraction on the bottom. And then we put moles of the substance we want to get to, which is HBr, on the top. And because their coefficients are both 1, it doesn't matter where you put it. It's a 1-to-1 ratio. And then we have we want to convert from moles to HBr to liters of HBr, and that'll be the final step. So when we do molarity, because we want to go from moles to liters, we put liters on the top this time because we want to end in liters, and the molarity is always given, and so the molarity happens to be 2, just like this one. So so 2 moles goes on the bottom, and then 1 liter goes on the top. So we pretty much just multiply all the numerators, so we do 10 times 2, which is 20, and divide it by the numerator, which is only 2. So 10 times 2 is 20, divided by 2 is 10. So we have 10 liters of HBr we need. Or you could use M1V1 equals M2V2. And remember, you can always use this when it's a 1-to-1 mole ratio, and it was a 1-to-1 mole ratio. So again, we have this, you can tell from the formula because there's a 1 coefficient here, 1 coefficient here, and neither one has subscripts. So if we take out what we have, so we have these two values, and we need to calculate volume of 1, and then you can call this M2 because it's molarity of substance 2, or substance 1, and then we have volume of substance 2, which is 10 liters, and molarity of substance 2, which is 2 molar. So we plug it in our formula, just like so. And then, so to isolate V, we have to divide by 2. So we divide the other side, both sides by 2, and so we're left with V by itself, with 10 times 2 divided by 2. And so we do 10 times 2, which is 20, divided by 2 is 10. So that's how we got our answer. And so now we have example 2a. And so hydrobromic acid is titrated with equivalence with sodium hydroxide. What volume of 1.5 molar of HBr is needed to react with 120 liters of 1.25 molar of NaOH? And so so first we have to pull out what we have. So what we need. So we need volume of the HBr again, but this time we're just using different numbers. So off to the side you can write liters of HBr because that's what we're looking for. And we don't have volume of HBr, but we have molarity of HBr, and we have molarity of NOH and volume of NaOH. So we start out with what we have that's fully given. So we have volume and molarity of NaOH. So we start with that. So we go first from liters of NaOH, and we use molarity, convert it to moles. So remember, molarity is 1 liter per X amount of moles. We want liters on the bottom so it cancels out. We're left with moles. So NaOH molarity is 1.25. So 1.25 moles per 1 liter. So we write it like that. Liters cancel out. We're left with moles of NaOH. So that's good. And now we go from NaOH to HBr, moles of HBr, using mole to mole ratio. And because it's the same equation, it's a 1-to-1 mole ratio, and NaOH goes on the bottom, HBr goes on the top because you want NaOH to cancel out. So we just write it like that. And so now we're in moles of HBr, so now we want to go to moles to liters, and we use molarity. So we put moles on the bottom this time because we want that to cancel out, and liters on the top. And remember, molarity is 1 liter per X amount of moles, and it's always given. So molarity right here is given to us, and it's 1.5 moles per 1 liter. And so we practically just multiply the numerator, so 120 times 1.25, and just divide by 1.5 because these ones don't do anything at all. And so if we do that, we get 100 liters of HBr. And now we're going to do the same problem, but we're going to use M1 or MA M sub A V sub A equals M sub B V sub B. And so this is the same formula I showed you before, and it's often much easier than doing all the stoichiometry, but both of them get to the same answer. And remember, you can only use this shortcut when it's a 1-to-1 mole ratio. So here we do have a 1-to-1 mole ratio, so we can definitely use this. So we plug in what we have, and we do 1.5 moles of the first substance. So right here, we can call this one A, this one B. So we have B here, so we put these two next to each other and multiply them. So 1.25 times 120. And so to isolate V volume of A, we divide both sides by 1.5. And after we do that, we get the same answer, 100 liters of HBr. And so now we have example 3, 20.4 milliliter solution of KOH was completely neutralized by 48.5 milliliters of 1.15 molar of HNO3. So, what is the concentration of KOH? So, in this one, it's again a 1-to-1 mole ratio, and you can tell by comparing the chemical formula. So we have KOH and HNO3 because we have one hydrogen here for every one OH here. So this is definitely balanced and it's fine. So we're gonna use the MAVA equals MBVB, and because again it's a 1-to-1 mole ratio, so we can only use it when it's 1-to-1. So if this was 2 KOH for every HNO3, then we couldn't use it, but it definitely is a 1-to-1 ratio. So we plug in everything. So, and it doesn't matter what you call which. So this could be A, this could be B. But remember, you have to put this volume with its correct molarity. So we don't have it. So 20.4 has to go with the unknown, and then these two go together because 48 milliliters of this solution, so they're paired up, and we do have that. And so to isolate M sub B, we divide by 20.4 both sides, and after we do that, we get M sub B equals 0.357, and so that is the final answer, or the molarity of KOH. And so now we have example 4, so this is our last example. So we have 159 milliliter sample of KOH is titrated to equivalence with 100 milliliters of 1.5 molar of H2SO4. So calculate the molarity of KOH solution. So we're gonna go instead of going from liters of A to liters of B, we're going to go from liters to moles and then use moles and divide it by the liters they give us to find molarity. And so just bear with me if you didn't understand that. So first we have to sort out what we have, like always. So we need molarity, so that's our final answer, so we can write off to the side molarity of KOH. And we have this formula, so it gives it to us. And we know that we cannot use the M1, M sub 1, V sub 1 equals M sub 2, V sub 2, because we have this 2 out here. So that immediately tells us we couldn't do it. And so we sort out what we have again. So we have unknown molarity and we have known volume of KOH, but we have known of molarity and volume of H2SO4, which is right here. And so remember, it's easy to convert milliliters to liters, and it really helps out when you're doing these problems because we're always using liters. So that's how we got these two. We just moved the decimal places 3 places to the left. And so now we start off with this one because we have it fully solved. So we're going to go from liters of this to moles of this. And so we start out with 1.1 liter of H2SO4. Use molarity, convert to moles. So remember, molarity, we want liters on the bottom, and it's always 1 liter per X amount of moles, and it happens to be 1.5 moles in this case. And so liters cancels out, and then moles are on the top, and there we go. So now we're moles of H2SO4. So step 1 check. Now we want to go from moles of H2SO4 to moles of KOH because we want to find moles so we can use in the molarity formula. So we use a mole to mole ratio to convert to moles of KOH. So we put moles of H2SO4 on the bottom because we want that to cancel, and we put moles of KOH on the top. And we get these 2 moles from the coefficient. So there's 1 mole of H2SO4 for every 2 moles of KOH. So 1 goes on the bottom, 2 goes on the top. So now that we're in moles of KOH, we're done with this part. So now we multiply all the numerators and divide by the denominator. So we do 0.1 times 1.5 times 2. And because the denominators are only 1, we don't have to do it. So we just do that and we get 0.3 moles of KOH. So now that we have moles, how do we find molarity? And remember the formula for molarity is moles of solute per liters of solvent. So the liters is given right here. So we have volume, which is liters, and we have moles. So we just take this and divide this 0.3 by 0.159, like just like that. And then after we do that, we get molarity, and it happens to be 1.89. So that is it for these problems. And so now there's a quick quiz to see what you learned. So when moles of an acid equals the moles of base, you have reached the A, titration point, B, the end point, C, equivalence point, D, neutralization point. And remember, the key word is equal. So which of the following answers sounds like equal? And that, my friends, is equivalence point, because it definitely sounds like equal. And remember, we only talked about 2 terms, so you can automatically eliminate down to B and C. We only talked about endpoints and equivalence point. So equivalence point, is when the moles of acid and base are equal. So we have OH and H plus are equal. So they're neutral. And then endpoint, remember, is when the indicator permanently changes color. So then that is endpoint. And then we didn't titration point and neutralization point, you can just ignore those. And so if 20 milliliters of 0.5 molar of HCl is titrated to equivalence by 40 milliliters of NaOH, then the NaOH concentration must be blank, 2, 1, 0.5, or 0.25 molar. And so